All right, welcome everyone to our live stream on Infrageometry. Today's going to be a quick one. Hopefully, we'll get into the depths of many of the things that we mentioned today later on. But to begin with, let's do a super fast recap of where we are. And let me double check that actually we're getting sound from you guys. Because there is, yep, it should be fine. Okay, just double checking. Um, okay, so as you all know, we are trying to figure out this discrete models for spaces and geometry with the intent of having a more computationally and formally established model or framework for the physics project and for all the research that's going on using hypergraph rewriting to describe physics and space-time, quantum mechanics, etc. So we have been stuck with a few issues in terms of how to model precisely for example, continuity of functions or continuity-like properties or smoothness-like properties of functions on these discrete spaces, and also how to make sense of the tangent-like structure of these spaces, which in some sense is everything about these spaces. But of course, we've made a great deal of progress just understanding that there is a very realistic chance that there's a theory for all these things, and we're just making sure that we have the right one. So today, I wanted to hear from Uti and his findings of he's been getting into hypergraph rewriting specifically and some of the algebraic structure there. So some quick recap and update on that will be great. And after that, I can show you my proposal for what could be an update on the discrete tangent bundle construction. So I think this edges as places idea that we had a couple of weeks ago really enables for a better and much more articulate, I think, model for at least the discrete tangents, the discrete tangent structure. So Udi, why don't you start us off, and then we'll take it from there.
Sure. But like the results that I sent you, I don't think they're exactly relevant to this project. I just wanted to like that was more for like the causality side of things. So I mean, I can still summarize it, but it won't be directly relevant to infrageometry.
Well, not directly, but they have to do with the hypergraph rewriting and the hypergraph isomorphism ideas, which are all relevant here. So just maybe give us a brief update on what you've been up to, and then we can quickly
Sure.
turn to
Um,
infrageometry.
sure. I mean, this stuff I have is just mainly definitions and propositions, so I can just say them. So it's like I've been trying to see the definition of causality in hypergraph writing, and in certain cases, the ordinary definition that is used, that if the edges are used by the new update rule, I mean, it kind of fails because you can have a hypergraph rewriting system where the rule does nothing, like it just takes an edge and just gives you the same edge. And so in that case, the second rule could have been applied regardless of whether the first rule was applied. And so there's I tried to formalize what an event is, what like and essentially an equivalence relation on the set of all events. And in the category of hypergraphs, you can like a morphism, you can think of that as an event, and then uh, there's an equivalence relation on the set of events that you can have uh, if the original hypergraphs are isomorphic, if the rule is isomorphic, so you can define what an isomorphism between two rewrite rules is using DPO, and then you can. Sorry, I just came running from somewhere, so I'm a bit breathless. But so you can do that, and then you can, what you can also define is that you have, let's say, you have an initial hypergraph, so you have the automorphism group of that hypergraph, and then you have, let's say, a rewrite rule, which is like H1 goes to H1 prime or something, which is some hypergraph rewriting rule, and then you can, using the definition of isomorphisms between rewrite rules, you can define what an automorphism group of a rewrite rule is. which is the set of isomorphisms from the rewrite rule to itself. And then it turns out that to completely specify the application, like to completely specify an event, you need the initial hypergraph, the subgraph that is being replaced as an ordinary double pushout, and the rewrite rule up to isomorphism. And then you need the isomorphism from the subgraph to the left-hand side of the rewrite rule up to the isomorphism of the rewrite rule itself. So it's like you're modding the automorphism group of the graph by the automorphism group of the rewrite rule. So it's like there's like some symmetry structure in the rewrite rule itself, which will basically tell you that up to this thing, up to this relation, no matter what the isomorphism you choose from the initial graph to the subgraph, so from the LHS of the rewrite rule to the subgraph, you will get the same resultant output graph. So that's how I specify an event up to this equivalence relation. And then I try to like, and now I'm trying to define what like the causal relationship between two events is. Like what does it mean for two events to happen in series and so on. That's it.
So what would you say is sorry, John, you want to.
I'm confused by many things in what you've just said. So you say you can define an equivalence class of so okay, I have a span, right, in my category of hypergraphs, and you say you can define an equivalence class of spans via DPO. How?
So let's see. I define an event. So like I did not like define this in terms
before let's ignore events for a moment. You said you can define an automorphism group of a span.
I can define an automorphism group of a rewrite rule,
which is a span of monomorphisms.
Okay. And
hang on, wait, sorry. Is it not? Okay, wait. Clara,
okay.
are we using DPO formulas or are we not?
We are, but I have
okay,
not.
So what is an automorphism? What does it mean to construct an automorphism group of a span of monos?
So okay, disclaimer. I did use DPO, but like I did not use the category theory language. I just used set theoretic language. But I'm pretty sure that it translates directly. So I can tell you the set theoretic definition, and maybe it does correspond to an equivalence relation of spans.
Okay. The set theoretic definition is this. I mean, the set theoretic definition is just graph inclusion relations, which is the same as the.
Yeah, so it's like a rewrite rule. You first remove the edges between the graph that you're trying to replace in the subgraph. Then you glue the new graph, and then you delete the vertices that are not being used in the output, like in the.
Yeah, okay, fine. So I know. So all right. So even if you want to say it set theoretically, right? I have an interface graph. I have two left cancellative inclusion relations of that interface graph into a left-hand side and a right-hand side. What does it mean to construct an automorphism group of that pair of inclusion relations?
It means that.
And how does DPO do that? Do you have an implementation of this? Like, can we see how it works?
I don't have it in code, but I can show you the formal definition if that will help. If that will help.
Well, yeah. I mean, you were giving a formal definition, but I don't understand what it means. Can you clarify?
Yeah, sure. Let's see. Okay, so. Okay, so blah, blah, blah. Okay, so this is how I define it. If you have a rewrite rule, H1 goes to H1 tilde, and H2 goes to H2 tilde, they're isomorphic if there exists an isomorphism between the left-hand side of graphs and and a bijection from the set of new vertices that you're creating. So the things that you're like taking the disjoint union with, from H1 goes to H1 and H2 goes to H2, so that if the union of those maps is an isomorphism. So an example of this is like these rules are not isomorphic. So let's say you have 1 goes to 2 goes to 3, and you have 1 goes to 2 goes to 3, and this, okay?
Yeah.
Now, according to my definition, essentially what I'm saying is that you can simulate one rewrite rule with the other by just permuting the vertices in some way. So it means that let's say you have these two rewrite rules. So to define an isomorphism between these rewrite rules, I need to construct an isomorphism from the left-hand side of both of these graphs. So now if you see, the only possible isomorphism from this to this is 1 goes to A, 2 goes to B, and 3 goes to C. Like, do you agree with that?
Yeah.
Because so, and the only possible bijection from the new vertex set, so over here the new vertex set is just 4, because that's the only vertex you're adding. And here the new vertex set is D. The only possible bijection is 4 goes to D, obviously. But then the resulting induced map, which is defined, so you define what it means for this
Yeah,
thing.
I understand why these are non-isomorphic in that definition.
Okay.
I don't understand what you mean when you say that the DPO generates this automorphism group. And I also don't understand why it's an automorphism group in the category of I can see why it'd be an automorphism group in the category of graphs.
Okay.
But new vertices is not a strong enough requirement for an arbitrary hypergraph, right?
For the rule to be an isomorphism?
Yeah, so again, it seems as though you sort of decided to use this set theoretic formalism. Okay, so you have an interface graph, let's say you have these two left cancellative injections into a left-hand side and a right-hand side. The left-hand sides, okay, the left-hand sides of two pairs of these two pairs of these inclusion relations. The left-hand sides are isomorphic. You want to determine, the point is that you can still have the new vertices be mappable like this in a way that the union of the rules is an isomorphism without the interface graphs themselves being isomorphic. At least for hypergraphs.
I think these work for hypergraphs. Would they not?
Why? I mean, scroll down to your previous example. So if I'm making a distinction between vertices and say one edges, then I could make every vertex here a one hyper edge.
Sure.
Then they're non-isomorphic by exactly the same reason that you gave before. But the thing that's being generated is not a vertex; it's a one hyper edge.
Okay, so you're saying that in like hypergraphs, if I treat the vertices as one hyper edges, then this definition would fail. Is that what you're saying?
Well, I mean, I don't know what it means for a definition to fail, but whatever intuition you're capturing obviously won't work as you go to higher rarity. And in general, I don't know if you tell me you've got a structure which you are calling an automorphism group of a rule, then I would want it to be I would want it at the very least to induce an automorphism class for both the L, R, and K of that rule, which this doesn't, as far as I can tell.
Okay, so I don't fully understand, like I fully don't understand DPO, I just know the gist. So maybe this doesn't hold in the more general case. So I will try and see how DPO will fit in this. And
okay, but I mean, so like an obvious thing, which I mean, so I assume you've checked, like, because again, what I would ideally want from a definition of a rule automorphism, which is the definition that would exist in compositional graph rewriting, is if you take any element of if you take any element of an automorphism group of G and you apply the K goes to L, K goes to R rule, then you will always get an element, or any element of that, of the automorphism class of that rule, you will always get an element of the automorphism class of H.
Yeah,
right? Which
okay, yeah, I agree. Yeah, that was the intuition I used also.
So do you have a proof of that here? I mean, I'm pretty sure that can't be right in this case.
Okay, let's see. Okay, over here, the fact that I mean, I did use like hypergraphs over here. Like as you can see, edges are just tuples and tuples, ordered n tuples. And I mean, the proof worked regardless of whether.
Sorry, proof of what?
Proof of
okay.
This is an equivalence relation. Sorry.
Well, yeah, no. Yeah, it's definitely an equivalence relation. But as I say, do you have a proof of the basic statement of what it would mean for it to be a rule automorphism? That is, you have a rule that takes you that way you can apply a rule from G to get H. Do you have a proof that if you take an automorphism, an element of the automorphism class of that rule, you apply it to an element of the automorphism class of G, you will get an element of the automorphism class of H?
So you G and H are two graphs, right? And
yes, do you, right?
Can you repeat it again? Sorry, and can you clarify what H
well,
and G are?
Maybe we're talking about completely different things.
Okay.
A rule automorphism to me would mean I have a rule. I can apply it to get me from graph G to graph H.
Yeah. Okay.
If I take an element of the automorphism class of that rule, I can use it to get to, from an element of the automorphism class of G to an element of the automorphism class of H. And crucially, that will always be true, right? So
what do you mean an automorphism class?
Sorry?
So you have G to H and then you take another, and then you take some rule that is isomorphic to G to H, right? And then you saying that you're applying it to a graph.
G to H is not a rule. G to H is a hypergraph production. That's an
okay.
Right? The rule is L is K goes to L, K goes to R. Okay. You then expand that to a graph production or hypergraph production from G to H.
Okay.
The point is that then if I take an element of if I take any rule that's automorphic to or isomorphic to K goes to L, K goes to R, then I should be able to apply that to any hypergraph that's isomorphic to G and get a hypergraph that's isomorphic to H.
Oh, okay, I see what you mean. So in set theoretic terms, you have a rule that goes from H1 to H1 prime, and then you apply it to some graph G, you get graph H. And then you're saying that if I have a rule that's isomorphic to this rule, then if I apply it to, then for any automorphism, sorry, for any graph that's isomorphic to G and any graph that's isomorphic to H, I should be able to modify the rule so that I get H prime, is that what you're saying?
You should be able to modify the rule so you get H prime.
Like to get like an isomorphism or something like.
H prime is the right hand side of the rule. What?
No, H prime is like the graph that's isomorphic to H.
I see. Sorry, I thought you said H. Okay. Oh, it was H1 prime was the right hand side.
Yeah, H1 prime is the right hand side.
Then yeah, I mean there exists a graph production from a hypergraph production from a graph isomorphic to G to a graph isomorphic to H for any element of the automorphism group. Or any element
I see.
I mean the fact that it's a group doesn't matter. I don't understand what else it would mean to say that you have an automorphism class of a rule.
Okay.
Are you using some different definition?
So what I'm just using that if you have a graph, let's say if you have a rule H1 goes to H1 prime and H2 goes to H2 prime, then in English, what it means for them to be isomorphic is that you can like permute or like you can construct a graph as isomorphism from or like you can take a graph that's isomorphic to H1 and induce that isomorphism on the right hand side of the first rule H1 prime so that it gives you the second rule.
Mhm.
in a sense.
So, Jonathan, one quick question is that notion of equivalence between rewrite rules, which I also agree is the natural one, corresponding to some, is there some, because I don't remember seeing this result where you connect that definition to some kind of diagrammatic span isomorphism.
No, so that's not. I mean, that's something that is discussed, but I don't think it's particularly well formalized.
Right.
But yeah, I mean, so yeah, what you'd be doing in that case is, yeah, I guess defining some kind of natural transformation on your, on some, yeah, on your category of graphs and injections. But yeah, the details of exactly how that work are a little bit unclear to me.
Yeah, same. Yeah, okay. Yeah,
But I mean, it's an interesting concept. I guess the concern I have is, yeah.
Sorry, I think I have a way to say it. Or maybe not, because English is my second language. Okay, anyways. So you have H1 goes to H1 prime, and you have H2 goes to H2 prime. Write it in a commutative diagram way without, and now I'm going to construct the arrows on the vertical side so that the diagram.
No, we understand that it induces a corresponding isomorphism. Yeah. The problem I have is that we already know from compositional graph rewriting, amongst other things, that just knowing H1 and H1 prime is not sufficient to define a rule. You also need to know the interface graph. And so
the subgraph essentially, right?
Yeah. So the point I'm making is that it's not at all clear to me that just because you can induce an isomorphism between H1 and H1 prime means that you can induce an isomorphism between the corresponding interface graphs.
Oh, I see what you mean. No, that's not. I'm not saying. Oh, okay. I see.
Because if those
you definitely need
then the rules certainly aren't isomorphic in any useful sense of that word.
Oh, so in my definition of isomorphism, I'm not saying that if two rules are isomorphic, then you'll always get the same output. That is not what I'm saying. I'm saying
no, of course. You're saying that you can induce an isomorphism.
Yeah, but you also need the isomorphism to the interface graph to completely specify an event, like to completely specify the output graph.
But I can't see any interface graphs in what you've written here.
Okay, well, let's see.
Yeah,
okay, so here's where I put the interface graph thing. Yeah, okay. So you have this rewrite rule. So you don't focus on the larger graph. This is the graph that you're applying the rule to, and this is the interface graph. And this is an isomorphism. Then what you need, so if you have this, then you know the production. Okay.
Sorry, you have an isomorphism into the interface graph from the left-hand side of the rule.
Yeah, like to the subgraph, yeah. Don't you need that, or what else do you need?
You would normally have an injection from the subgraph into the left-hand side.
Yeah, because multiple vertices
can
every single one, right? Usually.
So you have an injection from the interface graph to the left-hand side of the rule.
Yeah.
And and that will also specify what the production is. But in that case, you won't use the entire rule, right? Like, I mean, is that how DPO works? Like you have a injection. Why do you have an injection? What's the reason behind it?
So you need to know, I mean, intuitively, you need to know how the interface graph glues into the left-hand side.
Yeah.
And then you need to know how the interface graph glues into the right-hand side. And then that combined with a specific match, i.e. with a specific injection from the left-hand side to your graph, is sufficient to determine, to specify up to natural isomorphism what your I forget what you're calling H prime is.
If I have this rule and I'm trying to apply it to some graph, then you're saying that I can replace an edge using this rule also. Like I can,
So-
if I haven't.
So right now, in that, the way that the Wolfram model function handles this is that the interface graph is implicitly specified using the vertex names, in a sense, right?
Yep.
So the fact that one in the left-hand side is named the same as one in the right-hand side is kind of implicitly specifying an interface graph. We already know that that fails. I mean, in the general case, right? That fails in the case of hypergraphs. And there are even some pathological cases where I believe it fails in the case of graphs, although I can't immediately think of a counterexample. Which is partially why this, that's kind of partially the reason for doing this causality project, right? Is to try to construct the notion of causality that doesn't depend on token names, because those are effectively arbitrary, as you kind of alluded to. Start.
Okay.
Yeah, just to just to refocus the conversation, because we have limited time. I thought, because I thought that we were going to discuss something brief about the causality that might be useful for the specific hypergraph rewriting that we might be using in infrageometry. So I don't know if, Udi, you have some sort of compact insight on that, or we should just move to the infrageometry specific topics and maybe.
We should do a. I mean, this is pretty interesting, but I think it's quite clear that it needs further discussion.
Yeah.
So I mean, I like this direction. To be sorry, I know I sort of seemed overly critical. It's just like this is.
No, I understand your point. Like, okay, I should not have said DPO, because I'm not familiar with DPO. I just got some interesting results in the set theoretic case, but I'll try to generalize it to DPO. Like, I'll see how that works. So right now, whatever you say,
again,
like,
you don't need to use the category theoretic terminology if you don't want to. But the point is, even for non-compositional graph rewriting, we know that you need to know about the interface. In other words, you need to know how the you need to, when you extract out the subgraph that's isomorphic to the left-hand side, there is, even if you know the vertex, even if you have vertex UUIDs, there are still cases where there's ambiguity in how the right-hand side gets glued in, and that reason is why that fact is why you need an interface.
I did not know
pair
that.
of injections from the interface graph.
I did not know that. I thought you only need to know the vertex side. Okay, I see.
So this, as I say, I think this is going on along interesting lines. I would love to see a way to induce a true isomorphism between between graph rules. In other words, so for any span of monos in the category of graphs, or actually probably in general, I mean, we know that you can do DPO in any topos, because all toposes are a T7, or indeed any subcategory of a topos. So if you manage to show that there's a way to do that, then you could, that notion of rule isomorphism would work not just for graphs and hypergraphs, but it would work for like Riemann surfaces and other things, right? It'd be pretty cool. But anyway, sorry.
I mean, definitely, I will need your help in this, because I'm not familiar with the category theoretic language, and obviously the set theoret. I mean, my intuition fails, so I will need some extra input like today. So
sure.
Get another live stream.
Let's do that.
Yeah. Just before we move on, when you said, Jonathan, when you said that the Wolfram rule model, the way it's currently supported, what is it specific that it fails, that you said?
So you can have a situation where because effectively the way you resolve this ambiguity of how you glue in the right-hand side of the rule is just using vertex names, right? So all that it's really doing is you're essentially taking a union of two lists of edges, and then you're just deleting duplicates, so any vertices that have the same name get effectively merged. The problem is that vertices are only. It's like the conversation we had about the hypergraph packlet and whether you should treat vertices as a special case, right? The vertices are just one level of granularity, right? That you could also imagine a situation where you have several edges that are all nominally, two edges that are all nominally the same, but because the corresponding vertices don't have the same name, they don't get merged. but they should, right? And so in a framework that tracked the interface graphs, they would. So the point is that there are ways. Let me think of another example. Okay, very basic example would be imagine that you have, I say very basic example. Imagine you have you have rules that are applying to graphs that have some symmetry group, right? So that you've got some kind of lattice, like a pentagonal, hexagonal lattice or something, and you're applying rules to that. So when you extract out a subgraph that's isomorphic to the left-hand side, there is clearly some ambiguity. If each element of the symmetry group it gives a different way that you can glue in the right-hand side, and for a general symmetry group, you can doing the merging using the vertex names gives you a way to specify a possible gluing for every generator of the symmetry group, but not every element of the symmetry group in general. Yeah. So in other words, there are some gluing transformations from the right-hand side into the graph that you just can't specify if you only know, if you're only doing the merging based on vertex names.
Mm-hmm.
We need an example because I'll
I need an example. So.
Yeah, I think because I when you mentioned it, I was thinking this probably relates to because all the rewriting that when I'm thinking about rewriting, I'm thinking in terms of labeled hypergraph rewriting, just precisely because I want to avoid this kind of subtleties. So if you actually think of labels as being this extra layer of data on top of your sort of skeletal set theoretic hypergraphs, then these things don't become an issue. So if you have so in terms of the implementation, I don't mean mathematically. I mean mathematically it is where it is, but in terms of the implementation, you just have a way of saying, well, if there's a match that actually supports the labels, and the labels, by the way, have data structures, so that there's symmetry considerations that go into them explicitly, right? So that basically solves the problem. Now, obviously, the trade-off is that you now have to keep track of labels, which is an entire industry on its own, right? But that's why I've been sort of pushing for the hypergraph backlit to be by default tracking labels, and you can always sort of ignore them and just do sort of the set theoretic like rewriting. But the labels, so there's two justifications for labels, by the way. There's one is that one, the fact that you are able to overcome some limitations in terms of identifying symmetry subsets and things like that. And then there's the other very obvious advantage, which is that if you are going to, it's actually in disguise the same, but more explicitly, when you construct operations in your compositional structures of graphs, like the traditional graph composition in the usual classical sense, right? You want to specify that one graph composed with the other in a certain order, because especially if they are directed graphs, this is very relevant, right? That one graph composes with the other. So the way you accomplish this is basically by labeling, by saying, this edge goes to this graph, this edge goes to the or comes from this graph, whichever way you want to see it, and that is effectively a label. You can do that abstractly, or you can just explicitly state that this edge comes from this graph and therefore is labeled A, and this edge comes from that graph therefore is labeled B. So it has a lot of advantages. So I imagine that it will be good to see, as Nick says, an example, and how the conventional Wolfram model fails, rewriting there fails, and how some other options with maybe labels or some other naming, local names, local isomorphisms, because we were thinking about those as well, right, Nick, with all the how to do the local naming for local symmetry.
Just a good example why math fails, Wolfram model fails, and why, for example, hypergraph packet does not.
Yeah.
So there are, you can easily look this up, right? Because this is the distinction between SPO and DPO. Mm-hmm. So in single push-out rewriting, your rule is just a partial morphism from L to G, or from L to R, and then your match is a injection from L to G. And then by pushing out that span, you get a map from G to H, and that's your graph production. But it's known that that's not sufficient to characterize all possible graph rewrites. You need DPO, you need the interface graph. So in a sense, what one is doing with the current design of Wolfram model, and therefore, I guess by extension, the design of the hypergraph packlet, is you could almost think of it as like you're doing DPO, but your interface graph is not a graph. It's a discrete. It's just a collection of vertices, or a collection of vertex names. It's effectively just an index set, and you've got an injection from the index set to L, and you've got an injection from the index set to R. But that is equivalent to doing SPO rewriting. The index set is not really contributing anything, so to speak. Yeah. I can try and construct one, but it may be easier if you can just look up cases that DPO can handle that SPO can't handle.
Okay. So are you saying that gluing? So we're just, as you said, we're just gluing over vertices when we add the rule. We induce an equivalence relation on the vertices, which then induces an equivalence relation on the edges also.
Right.
Because edges are treated as a collection of vertices. So are you saying that we should not do that? We should label the edges also or something? Or like the equivalence relation will be generated by the vertices?
I guess I'm saying what I would ideally want to see is something that explicitly specifies. So in the rule specifies the equivalence class of subgraphs to which it applies.
I see.
Which is what the interface graph would do.
I see.
But wouldn't this be equivalently captured by having some constant subgraphs that are otherwise labeled? Because that's the whole point. If they're unlabeled, there's no way to do this, obviously. But if they are labeled, you label something, C for constant or whatever, or K for better names or whatever, and then and then you keep that graph, and it appears in both, and so you have your injections as you want, right?
I think so, because I think that that's equivalent, right? You need to specify. Yeah, I guess that's another way to think about it. Which is that it's sort of just having L to R underspecifies what things should be kept invariant versus what things are allowed to be rewritten.
Yeah.
Right. In the definition, I use the things that were allowed to be rewritten is essentially like up to like the isomorphism group of the rewrite rule.
Mm-hmm.
You can do that thing. You can rewrite. So you actually don't need the complete isomorphism from the subgraph to the rule, or sorry, from the left hand side of the rule to subgraph. You need it up to like the isomorphism of the rewrite rule.
Mm-hmm. Mm-hmm. Fair enough.
Right.
But no, okay. I didn't realize we were going to be talking about this today. We should do a separate live stream about this.
This should be separate. Yes, I agree. So
I'll prepare some counterexamples, and we can talk about that.
Yeah, definitely. So how about we use our final, 10 minutes, 15 minutes to discuss the edges as places kind of consequence that I wanted to bring forth. So let me actually put this on the screen so everyone can see. Okay, so unfortunately we don't have time today, but as I said, we'll delve deeper into this in coming live streams. So in any case, in case someone in the live stream is not up to date, we have been thinking about this discrete geometry as emerging from some graphic structure on a discrete collection of nodes. And so our first guess at what the tangent bundle or tangent structure in general would be was to consider length one paths. And so I'm naming this now the naive analog of the tangent bundle, because this is sort of the pictorial, the obviously pictorial analog of the tangent bundle, right? So the tangent space, the naive tangent space, you would take all the outgoing directed edges from the directed graph induced by the undirected graph. That was the sort of connectivity structure. So if you take to heart this idea of edges as places, and you think that every edge in this graph, right, in the connectivity structure, is a place where you can traverse in your navigation, and your tangent structure is effectively the infinitesimal journeys that you can take. So the smallest length paths that you can take. My suggestion is that you actually take the midpoints of these edges. So you create, this is what I said last time, right? That you have some new vertices in your graph, which are effectively all the edges, right? And then your tangent bundle just becomes, so sorry, the arrows are not showing here because unfortunately half of my keyboard actually stopped working now. So I only have mouse from now on because I spilled some.
The yogurt has done its damage.
Yes, so it worked fine, but then after 10 minutes or so, it started seeping into the electronics, and half of the keyboard is unusable right now. So anyway, but the idea is that you make your edges new vertices, and so you think of this graph that I show here as the places graph where you can actually traverse, right? So maybe we want to make the definition of a path to be between space points, so to speak, so vertex points, so to speak. But the important thing is that there are edge places that you traverse, which is in the binary case, it's absolutely equivalent to saying, you can only connect the vertices that are connected by an edge. So it's an equivalent statement to that. But what is very important in terms of the graph rewriting approach, or the graph calculus approach to the tangent bundle and to the vector calculus that we want to develop, is that now the tangent space at a point, and unfortunately I can't draw this because my keyboard is dead, that you have from each special vertex, you have arrows to each of the midpoints, right? So each of the red dots here will be the heads of the arrows coming from each of the spatial vertices, right? So these are the shortest paths. It's the same definition as before, actually. Here, the shortest length one paths, but based at vertex points, and therefore always pointing towards some edge point, right? So there's two or three immediate advantages of this perspective. One, it gives us a very natural definition. So first of all, there's a distinction between vertex places and edge places. This is something to be mentioned. I mean, there can be an edge place that is both, because there's a one edge for some reason, but in general, there will be a distinction between vertex places and edge places. What is very interesting is that this really gives you the sense of infinitesimal displacement, right? Because two vertex places are sort of an integral displacement, right? That you've covered some finite ground. But if you only move from a vertex place to an edge place, that's an infinitesimal displacement, right? So it's a very natural thing to say that if you have a path that goes from this vertex to that vertex, its derivative, right, the sort of tangent of that path is the edge that goes from the vertex node to the edge node, right? So it's a mathematically, it's like a formally different edge. It's not, we're not having these duplicates of everything is sort of superimposed on the same graph, and we have to start labeling because otherwise it's going to get kind of complicated. So that's the main idea, right? So the other thing that makes very simple is that we can start to talk about parallel transport in a much more precise sense, because there is now sort of privileged. If you think of the graph as just a graph with all the edge places and the vertex places, there are now subgraphs, directed subgraphs that represent vectors, and others that represent paths. So it's actually viable for us to think of interactions between paths and vectors, which is essentially what you want to do in parallel transport, right? And so this just gives you the articulation to possibly do that. And then of course there's the other added advantage that when you go higher order, when you go hypergraphs, this idea applies no problem, right? You have higher order edges, so each edge has a place node, and you can traverse over there. So all the discussions that we were having of this, maybe we can show that. Maybe we have the same. I mean, it's all blurred out here, but this picture here that is showing exactly, that you can, if you have a triangle and you have the only two edges, you have one path that goes through the triangle and another path that goes along the binary edges, right? So, so this is just paths on a graph in a technical sense. In a computational sense, we're just going to be looking at paths on graphs. There's really nothing more to that. In terms of, so in particular, all this implementation in terms of rewrite rules and, composition of vectors and addition of vectors, subtraction of vectors, reversal of vectors, all this kind of stuff just applies. So everything we discussed before actually is useful. We do it correctly, or at least in principle correctly. We just need to change our perspective that whenever you define a space with some hypergraphic data, that's going to define a graph of places that are, and not all places are equal. There are sort of landmark places, which are the vertex places, which are the sort of integral displacement locations. And then there are the intermediate points, the betweenness kind of places that you represent as the edge nodes in this sense, right? So, and of course, obviously, on top of everything that we just said last time, you also have a model to do continuity and to have something like functions that have smoothness properties or continuity properties that are that now just have again a direct place to take values on. So now you have an actual set of points. You don't have to distinguish so much about vertex or non-vertex. You just need to assign values to all these new nodes, and then it's just a matter of how you assign values to those nodes and the connectivity relations that exist between them that defines more or less continuous, or whether we want to make assignments of not just values but ranges or sets of values and things like that. It's also natural there. So anyway, I think this is the natural conclusion to, or the natural, what follows naturally from the edges as places, and it just gives a much clearer picture on infinitesimal vectors in a discrete context. And yeah,
that's very cool. I mean, so does this therefore accord with our early intuition about edges without sort of vertex endpoints being like the analog of open sets?
Absolutely, that's right.
Right.
That's right. Yeah, exactly. So exactly. Actually, thanks for reminding me of that, because because you can, yeah, precisely. Sorry, that's a great addition, because you can just take the sets of edge places that are connected to a vertex. That's effectively the definition of a neighborhood, right? That's the definition of a sort of a smallest neighborhood that you have in your space, which is going to look very diverse. In some places, like, I don't know, here, it's going to look just two dangling edges, binary edges. In some other places, it's going to look like a mess of higher order edges of all kinds, right? But that's where, that's where it should be, right? I mean, if you're in a discrete space, it's not going to look like a smooth ball or something that, as we are used to from geometry. It's going to be a representative of what's locally involved there, right? So I think it makes a lot of sense that it has that. Yeah, I think I'm coming around to the idea that edges, and the fact that vertices and edges are different, right? The edges are in principle collections of vertices in the simplest sense. It's actually going to pan out exactly for what we want. And I think in the previous implementations, we were somehow not working along that fact, or we were working a bit against that fact, and we were trying to force things a little bit outside of that perspective. I think this, to me, makes more sense. And just to reiterate what I said last Friday, we need to think that this could come from two different places, right? You could be thinking of these discrete models as being generated by some rewrite rules in some generation model, or it could be that these are discretizations of and partial information about other more refined geometries, right? So in either interpretation, it makes sense to say, well, these are my nodes of definite information or constraint points or whatever you want to call them for the coarse graining, and then you do a relational. So you do sort of a coarse graining in terms of just locations or the blunt sort of coarse graining, and then you do the relational coarse graining, right? Which is you parse your system as for the relations between the things that you just coarse grain. And in typical finite difference elements or finite element techniques and so on, you might want to voxels and then do the interfaces and so on, so your relations look like a grid or something like that, right? But in general, that you could imagine generalizing that idea and just in general thinking that you have some discrete elements that are somehow the base coarse graining, and then there's a relational past which effectively defines a hypergraph on those discrete elements, right? So anyway, just to emphasize that, I think it makes a lot of sense. My sort of bottom line, what I wanted to say is that it makes a lot of sense to consider edge places and edge structure as something that is sort of in a level above. So you would have your base manifold M here, what I call M here, this undirected graph, and this construction will effectively define, I mean, if you're technically defining the tangent bundle, maybe you would imagine the directed graph that has all the arrows pointing from the gray nodes to the red ones, right? And so that will be the tangent bundle. And that looks much nicer because, you don't have this uncomfortable fact that infinitesimal vectors were pointing between complete paths, right? That was, I think, a little bit uncomfortable. This feels, at least conceptually, much closer, but I think there's a lot of formal justification of why it's a good idea, not just because it looks conceptually more natural.
Yes, no, I mean that's really lovely. I really like the idea of there's a kind of, there is a uniquely defined endpoint, but the arrow itself is not an arrow to that endpoint, right? It's an arrow to some intermediate object, which in this case is sort of is the edge. That's really nice. I mean, I almost wonder. One thing that might be kind of interesting to look at some point, I mean, it may be totally stupid, right? This may be the wrong correspondence, but try and figure out, okay, so obviously in non-standard analysis, right, in things like Robinson's original axiomatization, you construct this hyperreal field, which is, I forget exactly how it works, but you mod out by some ultra filter of the power set of the naturals or something. But anyway, you get this field that contains real numbers and these other things, which he interprets as infinitesimals, and shows that they satisfy the kind of the algebraic axioms that you would expect infinitesimals to satisfy, that epsilon squared is equal to 0 and all that kind of thing. One thing that'd be interesting would be to work out if there is any connection between our, if we imagine scalar fields as being defined on the vertices and taking it, so each vertex has a value. When we take if we no longer think of the graph as just being a collection of vertices, but we actually include this edge structure, is there some sense in which that's formally analogous to passing from the reals to the hyperreals? And therefore, is there some connection that we can make to the non-standard analysis view of what an infinitesimal is? It may be the answer is no, but it's
no. I think I mean the direct analogy with the hyperreals or something like that, I don't fully understand, but I do see some parallels with finite field theory, right? Or the idea that you're thinking of functions, if everything is discrete in our setting, why would we just throw real lines, infinite information, real lines on top of our discrete model, right? I think we should be thinking of discrete values of integers, at least at first, integers or numbers.
Sure. No, I wasn't proposing actually recovering the hyperreal construction. I just meant that there are a bunch of So I mean, another setting in which I know this comes up is again in topos theory, right? You get these things called the McNeil reals and these topos theoretic constructions of the continuum, where you have this rather nice non-classical construction where you can define the infinitesimals as being the collection of real numbers that are not equal to 0 and things, and again that generates certain algebraic relations. So I guess to phrase my question in a less confusing way, I wonder if there's some way that just as we can imagine defining an algebra on vertices, whether we could imagine defining a corresponding algebra on the edges, and whether the relationship between the two would be formally analogous to the relationship between algebra on the reals versus algebra on the infinitesimals. That would be kind of cool. If there's some way that we can formally show that the square of any edge is empty or something, that would be kind of interesting.
Wait, Jonathan, the thing that you're saying, is it more complicated than like ordinary extensions of algebra where you're just saying a plus a epsilon where epsilon square is 0?
A plus a epsilon where what? Sorry?
So like, I mean, so whatever you're saying about the Magnus real, or was it Magnus reals or is it something else?
McNeil
Whatever
reals.
it is.
Yeah.
Yes, right. New reals and the other hyper reals. Is it more pertaining to this formalism? Is that what you want to get, or is maybe it can be something simple like just adjoining infinitesimals and just getting
Well,
the simple algebraic form?
the Robinson construction is a field extension. It's just
Okay.
it's just the ultra filter construction tells you which field extension to take.
Okay.
And so all I'm advocating is, suppose we have a finite field defined on the vertices.
Okay.
Is there some analogous field extension that gives us an algebra on the edges that sort of behaves like the algebra of infinitesimals in, say, Robinson, in the Robinson axioms?
No, that's what I was going to say, that it does look like a parallel, in my opinion. And it might be that if it doesn't pan out as an actual analogy, maybe it inspires how to define continuity conditions and things like that. Because I mean, at the end of the day, what we want to do, I mean, on the tangent side, I've been thinking of the preliminary, well, how to basically transport all the stuff that we did for the naive definition of the tangent bundle to this setting. And so far, I haven't seen any particular problems. I mean, I think there's everything, and also some advantages of, like, for example, sinks and sources are now much more natural because you can have arrows that point to the same vertex, or arrows that point to the immediate edge, but you don't have this issue of like arrows pointing to another vertex, and having this asymmetry between sinks and sources that we did have, right? So now you could imagine having something that points from just zero, and then it has pointing vectors towards it, or vectors pointing outwards from it, right? It's much more doable. But anyway, so I see that in the tangent direction being easy, but then on the function direction, we still have to make sense of what values we assign to the places, the edge places. Do we want to, as we said last time, consider ranges or subsets and so on? And one possibility will be to think precisely in analogous terms to that these are somehow refining. There's some vertex function ring, and then we are refining that vertex function ring by including elements or functions that will live in with things in between that represent values in between, right? So so at least for that, it will be interesting to consider, even if it doesn't formally establish a correspondence to something like that, or an instance.
Absolutely. No, this is really cool, and it's I like how it. I mean, it's in some sense it's a very, very simple switch, right? It's just a slight change in how you think, but suddenly, a lot of these questions about, yeah, exactly what you were outlining, right? The distinction between a path and its endpoint, right? Because what we want from a connection is something that tells you, if I go along this path, where do I end up?
Mm-hmm.
Well, in the previous definition, right, the definition of the path told you where you end up, so it kind of felt a bit hollow. Whereas this sort of, I mean, it still contains all the same information, but somehow you're treating the path as a fundamentally different object that does not a priori contain the information about its endpoint, and then somehow it's the connection that tells you, that tells you how those things glue together. I think that's really cool.
Exactly.
That's really cool.
Yeah, and I mean, it gives us a natural differential integral calculus language to speak about, right? Because it naturally tells us that, in this very specific binary sort of pairwise context, it gives us the notion of path as we had it already, but it also gives us the notion, which is the integral notion, but it also gives us the notion of tangent vector, which is a specific kind of path still, like before, but it is a very specific kind of one path, right? So it allows you to speak of this relation of, if you give me a collection of length one paths, right, do they integrate to a full path, right? That's now a meaningful discrete finitary question that you can answer, right? So that's exactly like what you want, because you want a finite model of the continuous case, which one of the main questions is always integrability all these structures, right? Curves integrate, or actions integrate into curves, or vector fields defining flows, and all those kinds of things. And now we have a sort of how to say a native hypergraph language, native hypergraphic language to express precisely those notions, right? So I would say that that's where we want to be. I mean, now we have to flesh it out, and in the next few days, actually, we have a long flight coming up, and I'm gonna be typing up all this stuff and like making the nice definitions in the tangent bundle. So hopefully in a couple of weeks I can give a sort of summary, and maybe sometime before Christmas, maybe even Stephen can check out and see how we're doing with this and have some updates.
Yeah, Steve, I gave Stephen the estimate yesterday that I thought we needed probably 1 or 2 more live streams before we really had something, something good polished. So I think after this, and maybe one more to hammer out these details, I think we're in a good shape to talk about parallel transport, continuity, the beginnings of continuity conditions, differentiability conditions,
For sure.
those kinds of things.
For sure.
Set that up. Yeah.
Yep. Sounds great.
Wonderful. Okay.
Now we just gotta do definition proposition.
Sorry,
say it again.
No, I was just saying now we just gotta do the definition proposition thing.
Yes.
Example definition.
Yes. But again, no, this is great. So yeah, let's let's try and set up a live stream. Well, okay, let's try and set up a live stream with Nick for maybe later this week. And Uti, we should do a live stream discussion about causality.
Sure.
It'd be nice to have Carlos there, but I understand Carlos is going to be busy for the next couple of weeks.
Yeah, if you schedule it, just schedule it, and I might be able to join, just because of how timing. Sure. Just don't count me in for the timings, but I might be able to join.
Yeah, all right. We'll hopefully we can have you there, but if not,
I'd love to be there.
Do a catch up once you're back.
It'll be very useful for me to follow. But I will catch up on the.
Carlos, how long are you? How long are you there in the US for? Like, how long are you gonna be busy?
So I will be. So the next infrageometry sort of get things together. I think we can do it at the end of next week. So if we are already happy to look at our diaries, my natural moment to meet will be Friday, because I think Thursday evening I technically could be available, but I don't want to risk some flight disruptions or whatever and them missing it. So Friday the 8th of December looks perfectly available for me.
Okay, that sounds good.
Okay, so I'll
I have yet to confirm. I have an exam.
You have an exam on the 8th?
Yeah.
What time?
It's fine. I mean, I think it's in the morning.
Okay. Yeah.
I'll confirm.
So if we stream around this time, should be fine, right?
One second. It should be over at 12. It should be over by 12 p.m. So I'll be free at 12 p.m.
12 p.m.
on Friday.
Central or Eastern?
Yeah, I mean 12 p.m. here, so 17 UTC.
Okay, sure. Yeah. We can have it sometime in the evening. 17 UTC or 18 UTC, something like that. So I'll make a preliminary note for 17 UTC like today, and I can send some messages, but we can preliminarily aim to meet there for infrageometry.
Okay, for sure.
All right, fantastic. Well, great update, and I will be in touch. We've seen you a bit less than usual in the next few days, but yeah, exciting times for the connections in the US as well.
Yeah. Well, yeah, thanks everyone for joining. Thanks, Carlos and Uti, for updating us. And yeah, looking forward to doing the next one of these.
Absolutely. All right, everyone. See you soon.
Bye.
Yeah.